Okay, so this is the last lecture in the semester, and the final is going to be on Tuesday, right? You guys all know the room. It's all on the registrar's website, okay? I think it's actually in here, yeah? I think that's possible. That's absolutely possible. And so everybody's in the same room for the final, all right? I would like to get started with the last two clicker questions, okay? So let me show you what they are here. This is number one. I'm just starting it here. The poll is open. You can take some time, okay? Take what about 2 minutes, okay? That's a fairly long one, so see if you can do it. If you don't get it right, you will still get, get like 70% of the point, right? Yeah, what are the products of this, what's the products of this reaction? You see there's options there, and then we pick two options, okay, on the right. Does that make sense? Yeah, good, because you only have 5 sources on the floor. Think about it, what is this? It's an old analysis, right? What's the double bond in here? There's oxygen there. So what do you form? Do you need another minute, or are you going to do 1 more minute, okay? We'll do 3 minutes. Let's see. It's not that hard. Another 20 seconds. Let's put in some choices, okay? Let's see. Okay, good. Let's see. Let's see what you guys predict. C. It must be, let's see, C is A and E. So A and E, that's correct. Okay? Good. It looks like you guys know what those analyses are. Okay? You basically take the double bond, cut it in half, right? And then where the carbon-carbon double bond was just place an oxygen on the double bond. Okay? So you get a carbonyl group, a CO double bond, either an aldehyde or a ketone. All right? So let's do the next one. This one. Okay, let me see if I can start the poll first. I can't. Oh, okay. Sorry, I think I stopped the poll. I'll start it again. Okay? So again, let's do 3 minutes for this one, the longer one. Think about it. Well, there's all the reactions you learn. Okay? There's those reactions you learn in chapter 8. And the question is, how do you go from that thing to that thing? Right? Left to right. What kind of reagents do you use? Try your best. Okay, this is a hard question. But remember what we talked about in the review session? One good strategy is you go for a double bond. Okay? You make a double bond and then you do one thing to it. Okay? Okay, guys, one more minute. Let's see. Oh yeah, you can only pick the one of them is correct. I don't know if you pick the only other which are correct. Okay, so yeah, if A is not there, it just means you don't need to pick A. Okay? That helps that rules out some things. Alright, so I think we can reconvene, okay? Another 15 seconds, and then let's discuss it. Okay. Alright, let's see. Let's see what you guys picked. Let's see. Let's see, I think B is the correct answer. So you guys actually, it's the majority line, okay? This was a hard question, so let me show you what's going on. All right? Let me just get the control here. So yeah, so B is the correct answer. Why? Again, general strategy here. We're going to talk about synthetic problems, right? That's frankly the hardest part, okay, of this chapter and everything we talked about so far, is now to combine everything you have learned, okay, and figure out how to apply a sequence of the reactions you have learned to go specifically from one compound to another, okay? And why do we care so much about doing this kind of retrosynthesis or synthesis planning? Because that's actually what organic chemists do, okay? Because what the goal is in the end, right? For example, you can take a computer program and you can predict, you can come up with a compound which might bind into a protein, into a pocket of a protein, and would be a potential drug. But then the job of the organic chemist is to synthesize the compound, okay? And you need to be pretty good at doing this synthetic strategy, right? To be able to synthesize drugs in new compounds. Otherwise, you can never make the compound. You will never have a drug, okay? It's that simple. So that's a very important skill. And that's frankly why you're learning all these reactions. It's not just to learn the reactions, it's to learn how to apply them together to make useful compounds in the end. Okay, so here's what happens. D as a B, right? You have, first step is H. So this is what? This is tibiotoxide, right? That's a sterically hindered base, so it will not act as a nucleophile, which is great. So it will act as a base, and so it will do this, right? The tibiotoxide will literally just take off. We'll do an elimination reaction, okay? An E2 elimination. And then in the second step, so after you do the E2 elimination, what do we form? I'll write it here. It's a little bit ugly, but it's okay. Right? If we do an E2 elimination, we get a double bond here. And now we basically just have to add, what do we have to add across the double bond? See, an H and an OH, so together that's water. So we have to do a hydration reaction. We have to add water across the double bond. And that's C, okay? You learned that, right? That's the mercuration, demercuration reaction, okay? Which adds the water across the double bond in a Markovnikov type fashion, right? Where the OH attaches to the more substituted carbon. So this would be condition C. Okay? Does that make sense? So it's just applying these reactions, but you have to be super proficient with all those reactions. All right? So we are finishing up. This is right, continuing now, right, from what you watched, those movies from last lecture. Yes, Caroline.
Would you be able to use NaOMe as well instead of terpene oxide?
Oh, okay, this is an awesome question. Okay, Caroline asks, could you use, I'll go back to the previous slide, very important, okay? Could you use, for the first step where we do the elimination, could you use NaOMe instead? What do you guys think? Who thinks yes? Who thinks no? So no opinion. I would say no. But what? Yes?
Is there also a strong nucleophile?
Yes, exactly. The problem with NaOMe, sodium methoxide, right, is it's a smaller species, so it's actually also a good nucleophile. It's a good nucleophile and a good base. And so what it will do is it will have two competing reactions there. You will get you will get some SN2 reactions, right, where you form the carbon O and E bond, and then you will get some elimination reaction. But you might get about 50-50 or 60-40. And so that's usually not very desirable because you lose 40% of your material and you have to purify it in the end, right, and remove the undesired stuff. So T-butoxide is better, much better in this case. You want to, whenever you do the synthesis stuff, you want to make sure you eliminate any possible side reactions as much as possible. Okay, so pick the best possible reactions which don't give you any side products, if you can. Okay, it's a very good question. Thank you, Caroline. Okay, so let's go back to this one now. So here we do synthesis practice. How can you go from left to right? So you guys thought about this, right? Because you saw those movies, right? Okay, so the question is, does anybody want to try it? If you feel brave enough to take my iPad and try it out. We're going to pretty much just do review problems, okay, from now on. We're going to do these two, and then we have the ones I posted last night, which are just the review problems from Sandy Werthman's section, like similar to the ones we did on Wednesday, just different. I think it's, rather than starting something new, we're just going to practice until the end of lecture and hope it helps you guys, okay? You want to try it? Okay, thank you. And then just, we're going to, so this is just a review session for everybody. Okay, so again, the general thing, okay? Because what you have learned, the two types of classes of reactions you have learned in Chapter 7 and Chapter 8 is elimination, right? SN2 reactions. And so you can make double bonds and you can add things to double bonds. So if something is switching around, going through a double bond is usually a good idea, okay? Mm-hmm. So I think Caroline is going to try to make a double bond. Okay? And so you're going to do T-butoxide, okay? Mm-hmm. Like before, that's a great base. Again, we want to use T-butoxide, not sodium methoxide, because we want to selectively eliminate. All right? So that would be, okay, perfect. So it's an E2 elimination, right? And that gives us this product. So that would be the first question mark, for the first product. Mm-hmm. Now for the second step, we want to, you look at what you need to add to the double bond. So that would be methanol, right? Pretty much. Mm-hmm. And we always said you can't add methoxide, right? So you have to use methanol plus an acid. Mm-hmm. And then the question is, can you do a rearrangement which will actually give you the product?
Yeah, so like right here I want to get to where it's a tertiary carbocation.
And then they will rearrange.
Yeah.
Or rearrange into a tertiary carbocation.
Yeah.
So try.
Okay.
Generally, you don't have much choice. You have to use methanol and an acid.
Okay.
That's what we always have used, okay?
Okay.
Whenever we added methanol.
So like NaMeO? I mean, that's not an
just
acid.
MaOH, MEOH,
Okay.
methanol, and then acid, so something like H2SO4.
Okay.
Or you could just write H plus.
MEOH. Sorry.
MEOH, yes.
Yeah.
What you cannot do, right, what you can never do, I would like not to see that on the exam, is something like you put MEO minus and then H plus, right? Because that's going to neutralize each other. It's going to react. You can't have a strong base like MEO minus, like methoxide, as well as a strong acid. That doesn't work. It's not compatible. So what you have to do is use MEOH and H plus. Right?
Okay.
And then the H plus, like always, will just protonate the double bond. Okay.
Okay. So.
So technically, what happens? I'm going to make it a little bit harder for you because somebody came to my office was asking about that. So technically, what happens if you have methanol as the solvent and you have concentrated you have sulfuric acid, H2SO4 in there? What forms?
The leveling? Is that the
Yeah, the leveling effect. So what actually forms out of there? Yes.
MEOH2 plus?
MEOH2 plus. Okay?
Okay.
So maybe make like an arrow from these two guys and say forms MEOH2 plus, right? And that's going to actually act as the acid. Okay? Because remember, that's the leveling effect, right? Because H2SO4 is a strong enough acid to lose all of its protons to methanol.
Okay.
So it just forms the protonated methanol.
So then can I just bring an arrow over to the MEOH2 plus?
Hold on.
Sorry.
Let me make a few. And I'll just rewrite it a little bit, okay?
Yeah.
Some people don't get confused. So let's see. First of all, your plus is just down there, so it should be this MaOH2 plus. Okay? And then we'll put the note, we'll say leveling effect, okay? Just as a keyword. All right? So far so good. Now what we're gonna do is I'm gonna simplify the whole thing a little bit, okay? Because this is gonna be a movie. I'll upload it after, so you can leave it in your notes if you want. But just to avoid getting confused, we're just gonna do literally like this. We're gonna just write MEOH2 plus, okay? That's the key species. So you don't even need to mention H2SO4 and methanol. You could just say you're gonna add this plus methanol, all right? This and MEOH, or H plus and MEOH, and now we're just going to continue with the mechanism, right? See, so you protonate it. I'll lead for it, so we save a little bit of time. So the product here, right, is our secondary carbocation, and of course now this is all set up. Remember, you have a H here, right, which is not drawn, and this is now we are all set up to just do this. Hydride transfer. Sorry, this looks a little bit, just the arrow looks ugly. Right, we do the hydride transfer, the hydride shift. Okay, and we do this. Now the H is over here. So we have two H's, the cation is over here. And now how do we finish it? Right, we have more methanol in the solution, which now adds in there. So we have MaOH. The MEOH, just a nucleophilic attack, and we're going to get OH, Me plus again, right? And we probably have to write this H out because we need to deprotonate it. There we go. Okay, so what is deprotonating it? What's the base? Must be again another methanol. Remember, that's the solvent, so you have plenty of it. So that will do the deprotonation. All right, and we're done. Okay? Good. Next one. Any questions? Let's do the next one. What you will see, the good news is it's always the same kind of things, okay? It's always a hydride shift, methyl shift, protonation of the double bond, electrophilic attack onto the double bond, etc., right? And then the nucleophilic attack of water or methanol and the deprotonation. Always the exact same thing, okay? So now, next one. This is a harder one. Does anybody have a solution for this? I on purpose didn't post a solution video, so. Anybody? You want to try? Yes. Again, go through a double bond. That's my strongest advice is whenever you have something you don't know how to do, make a double bond first and then add something. Right? And if you want to go from functional groups like OH or something, you make the double bond first and then you do a hydrogenation, right? Which adds 2 hydrogens and that will give you the same.
So I'm going to start with T-butoxide again. Just to...
Good question. So T-butoxide will not, what will T-butoxide do in this case?
Well, won't it... I want to do an elimination to start with, right?
Yeah. So you want to do an elimination, right?
Yeah.
So now the T-butoxide, what happens is, it's a special case of an elimination, okay?
Oh, so I need the special...
There's different ways you can do it.
Okay.
The easiest way is you just use H+.
Okay.
And so, but I want to show you what happens with T-butoxide. T-butoxide is a strong enough base, so it would literally just deprotonate the OH group, and it would make O- there.
Okay.
And then, you know, that's never going to leave. That's not a leaving group. So you would just form this thing with the alcohol deprotonate.
So then you want to just use H+ instead?
You want to just use H+. That's the reaction you did in the lab. Remember?
Yeah. Is this undo?
This one is undo. So what I'm saying is whenever you have an OH group, you cannot directly eliminate with a strong base because it will just deprotonate the OH group instead. It will not, OH is not a leaving group, right? So you have to convert the OH into a good leaving group, and you do that by adding H+. And I think you did that in the lab.
Can you also use the tosylate, like T? Could you also use the tosylate?
You can use the tosylate, and the way you would use the but I haven't shown you how to make the tosylate. I think the book has. So if you wanted to, you could. So you would use it as a base. You'd add a base, you would make O-, and then you would use the O- with tosyl chloride. You know, but you didn't learn those mechanisms, so I don't want you to get confused. The easiest way to do it, whenever you need to make a double bond out of an OH, you just add H+. Okay? That's what I would recommend. But yeah, if you make the tosylate and you do it correctly, and you read the chapter in the book, it's fine with me. I mean, I'm not going to penalize you for correct stuff.
Yeah. So then would my next step would be with the HH and the palladium and carbon?
HH and palladium and carbon, and then you're done.
Yeah, and then it just goes to this,
It
right?
just goes to the product. All you have to do is literally,
Yeah, that's all. Perfect.
Perfect. Thank you so much.
Should you also, when you do it, like draw, like here I did on my notebook, like I
Oh, the
did
palladium
plus
and carbon?
Palladium and carbon?
No.
Okay, you
It's
don't
a
need,
catalyst.
It's just given?
Generally, all you really have to do, unless I specifically ask for it, is just draw the organic product, right? That's fine. That's kind of organic chemistry. Yeah.
On the exam, if we have to draw like H+, is it okay to just write H+, or do we have to actually write an acid that we would get the H+ from?
It's okay to just write H+.
Okay.
But yeah, unless, again, I specifically ask for it, but I think the book, even in the solution manual and stuff, they just write H+.
Oh, okay.
That's fine.
Cool.
I think by now you know what acid to use. It'll just be sulfuric acid, right? So I trust you. If you just write H+ and you do the arrow pushing correctly, that's fine. All right. For a base, make sure you write the base, because for the base it matters whether it's sterically hindered or not. Sometimes, okay. So don't just write base. Write something like T-butoxide or methoxide or stuff like that.
In those examples, we also don't need to draw the counterion, right?
You don't need to draw the counterion. You can pick a counterion if you like. You can also not draw a counterion. That's fine. Okay. All right. So any questions? Yes. Isaac has another.
The acid, when it goes on to the OH, is there a hydride shift? How do you get what's the mechanism to get the double bond?
Okay, so Isaac is asking what's the mechanism, right, again, for the double bond formation? I'll draw that quickly, okay? And whether you can get a hydride shift. Okay, let's just do it like over here. So this is the start, This is the starting material, right? So let's say we just do it really simplified with H+. And so then we are going to get one of the lone pairs right here is going to get protonated. And so we go here. And you can even write it like this, OH2+. Okay. And now this is going to leave. And we're going to get a carbocation. And you're right, it's a secondary carbocation here. And so, okay. But you know, even if you did a hydride shift, you would still get a secondary carbocation again. You know what I mean? You could do this, and then yeah, the double bond would end up in a different position. But after you hydrogenate, you're still going to get the same final product.
Okay.
It doesn't matter where the double bond is.
Where the double
Because in the end, after hydrogenation, so you might get a little bit of rearrangement, but only a little bit, because it's secondary to secondary. So usually the rearrangements are very favorable if you go from secondary to tertiary, or primary to tertiary, right? If you make a more stable cation. In this case, that's not really the case. So what happens instead, right, is just then the water acts again as a base, okay? Because now we had a leaving group, so now you have OH2, and basically that takes off the H. So what's the formal mechanism? What's this kind of reaction? E1. That's an E1 reaction, okay? So that's E1. E1 mechanism, okay? Any other questions about these problems? Okay, is it good? So let's see. I have a little list here, about stuff which is really important in chapter 8, okay? This stuff is all on Blackboard, but you can take a picture if you want, that's fine. You can even take a selfie with it. Maybe not. But you have to be careful with selfies. People fall off mountains. Seriously, people try to take selfies and they fall off the mountain or something. So, okay, very important is predict, okay? When is addition favored, when is elimination favored? Okay? So write products of these things, right? Markovnikov, anti-Markovnikov, all the mechanisms there. Besides, I posted a list again of all these reactions as well on Piazza. Somebody asked for them. And some of the mechanisms you don't have to know, but it's only a very few of them. Like the mechanism for ozonolysis, you don't have to know. Okay? The mechanism for the sodium borohydride reduction, like for the oxymercuration, for the demercuration step, you don't have to know the mechanism. And the mechanism for the, let's see, what else you don't have to know? I don't remember. There's only very few things, special steps you don't have to know. You just have to know the reagents. But usually, you still have to know the first step, for example, for the oxymercuration, right? It's just the ones we didn't draw, the mechanisms we didn't draw and were specifically said in the lecture. You don't have to know those. You don't have to know those. But the other thing you have to be able to do, okay, in principle, is to take one mechanism and mix it up with another mechanism. So I might give you a new reaction. So for example, just giving you a simple example, if we did this reaction now just with methanol, right? I could give you a reaction where we do it, for example, with ethanol, okay, or T-butanol or something. We can change these reagents, right? Or if you can do it with methanol, maybe I could give a similar reaction with a dimethyl ether, right? You know what I mean? We can start to do similar mechanisms with slightly different reagents which are related, and you should be able to do that, okay? It won't be all like that, but there might be some challenge question, where I try to see if you can extrapolate. And that will be still fair game for me, okay? Just because you know those mechanisms in general, and then you can, the practice problems, there's also some things like that. Like reactions you have never seen before, but you can try to figure out how they function, okay? It's kind of like in math, you get some question, like about something related to what you learned, but it's not exactly what you learned, and you have to extrapolate, okay? Those will be harder questions. There'll be maybe one or two of those on the final. Acid catalyzed hydration, oxymercuration. So you have to know the mechanism for oxymercuration, but not demercuration. Hydroboration, oxidation. I think you have to know the mechanism for the hydroboration step, but not for the oxidation step, right? Catalytic hydrogenation, you should also kind of know the mechanism. Halogenation, you should know it. Bromohydrin formation, right? Epoxidation, epoxide ring opening. You need to know the mechanisms. Syn dihydroxylation. So here you need to know the first step, right? That's the osmium tetroxide reaction. And then the second step, the reduction, you don't have to know the mechanism, just the reagent. And ozonolysis, you don't have to know the mechanism, but you need to apply the reaction. And then the retrosynthesis is literally just combining everything together, okay? So that's formally the end of lecture. So we're just going to practice, okay? Going to keep practicing. Let's see. Let's complete these reactions. Can we just give the iPad around? You guys want to try? Or do you want me to write it? You want me to write it, okay? Okay. So what kind of reaction is this? This is, you see, the H plus is again acting as the, what is it doing? It's protonating the double bond, okay? Like always. So, doing again like this. Protonate the double bond. And bless you. See, This will make you feel good. This is like, look, it's always the same thing. So you get this carbocation, right? And you protonate it, and then the methanol, what is it doing? The methanol is acting as a nucleophile, right? Kind of like what we had before. So the methanol is attacking the double bond, like this. Sorry, I wanted to change to red. You're going to attack from here so it doesn't overlap with the plus sign. Okay, and then we're going to do this. You form the protonated methanol, right? Or the protonated methyl ether. And then we're going to lose the H+. I'll just say deprotonation. And finally, the product we are getting is this. So here's the thing. I'm writing out the mechanism here for you guys. But you don't, on the exam, you just have to write the product. Okay? Does it make sense? You don't have to, unless I'm asking for the mechanism, you don't always have to write the whole mechanism. Okay? Any questions about this one? Yes, please, Simon.
So this is obviously not a chiral center.
Yes, this is not a chiral center. Yeah.
But if it was, could you get like enantiomers from this type of reaction?
The question is, could you get enantiomers from this type of reaction?
Like if you had like a methyl sticking off somewhere.
Yeah. Let's see. So if you did something like this, then absolutely you get enantiomers. So if you did, let's say we did this. Okay.
Did it show up? Oh, there, right.
Yeah. So this one, and we like do the same kind of reaction. Okay, then you will form. Well, now you even can have diastereomers, right? Because the methyls can be cis or trans.
Right. Okay.
You see, in this case, yeah, see what you would form is this one. Plus this one, right, where the methyl is now on the opposite side. Okay, and now in this case, these would be diastereomers. Does that make sense? But yeah, and then if it were different, like it didn't have a second chiral center, then you would form enantiomers. And then, but in the one up there, it's not a chiral molecule, so you don't form the enantiomer. So think about these kind of things carefully. Okay, in my opinion, that's the hardest thing to think about. The stereochemistry. Okay, good question. So let's go to the next one. All right. Here, what is this reagent? RCO3H. This thing. That's a per acid, right? It has an extra. So RCO2H, that's just a carboxylic acid. Okay? So RCO3H, that's this thing. Okay? So it's a per acid. And what do per acids do? They do epoxidations, right? So then you should know the mechanism for this. Remember, the double bond is attacking this terminal oxygen, right? Like this. And that, remember, that oxygen is electrophilic because you have a good leaving group attached to it, okay? And then you get the intramolecular deprotonation, and this bond here is moving over here. All right? So you should be able to draw this kind of mechanism. I think last time I asked to draw the mechanism of this thing on the final. You guys saw it? So it's a cool mechanism, okay, which is a little bit different than all the other ones we discussed. So it makes for a great question. So what you get then is the epoxide, right? The epoxide is the three-membered ring. Okay. There we go. Done. Done. Does this have an enantiomer? What do you guys think? Absolutely. Because you see, this has a chiral center where the epoxide formed. So that means that the per acid, if it attacks from the front, you get one, and then you get the one I drew here, right? This is from front attack. And now from backside attack, you get this one. You get the enantiomer. Where now the H is in the front. The epoxide is in the back. Okay, so these are enantiomers. All right? On the exam, I'll try to be super specific. I will be like, in the question, if I want you to make sure that you write all the enantiomers, I will be like, make sure you write, all the stereoisomers, be special, to be very clear about stereochemistry. Okay? Then you have to make sure you do this kind of, like, really carefully analyze it. If there might be some questions where I just literally don't care about stereochemistry, and then you don't, I'll just put like ignore stereochemistry. Okay? But the majority of them I might not want you to ignore stereochemistry. Okay? Any questions? All right, so let's go on. This one. What can we do? Boration, or hydroboration oxidation, right? Why does it have to be boration or hydroboration oxidation? Why can't it be like addition of water or mercuration, demercuration? Because it's anti-Markovnikov. You see, if the OH gets added to the less substituted carbon in the end, then it's anti-Markovnikov. Then the only reaction you can use is boration, hydroboration oxidation. So what are the reagents? Right? It's the BH3 and THF, and yeah, that's number one. And number two is what? H2O2, the hydrogen peroxide, and OH minus. Okay, so basic hydrogen peroxide. Okay, and again, the key here is this is anti-Markovnikov addition. Okay? Oops, sorry. Any questions about this one? That's fine. Okay? So we're going to continue. So we get through these. What happens here? What happens here? SN2, right? So we're back in chapter 7 now. SN2. So you look at, again, how do we know it's SN2? You look at the substrate, primary, right? Good leaving group. And then you look at the nucleophile, or the reagent. That's a good nucleophile. Remember from this table I gave you? Sulfur compounds like RS minus or RSH. Those are great nucleophiles. So that's SN2. And so that tells you, all right, getting backside attack, but it doesn't matter here whether it's back or front side because it's not a chiral center, right? And we just get in the end, and then you get deprotonation, and you're going to get beautiful SN2 reaction, okay? So it's just going to be like this, SH. Sorry, actually this is SH minus, obviously, right? Because it's sodium SH, so it's actually sodium plus SH minus. Does that make sense? So it's really just one step. And then plus B or minus, but you don't actually have to draw it. Any questions? Caroline, yeah. Say again?
Why would you have chirality? Can you split it down the middle and have the same?
Oh, well, the question is why wouldn't it have chirality? Yeah, this thing is actually a meso compound, so it has a mirror plane going through the middle. But the thing is, what matters you see, I left this part alone. I didn't touch it. Even if it had chirality, you would just leave it alone. You wouldn't touch anything there. Because the SH minus is just attacking the CH2Br group. You see what I mean? And what I'm saying is the this carbon here is not a chiral center, so it doesn't matter there whether it's backside or front side attack. The rest of the molecule will leave alone, right? Make sense? Okay? So, next one. There's one more here. Okay, how to do this? Making two double bonds at the same time. How can you do that? Just shout. We did do elimination reactions, right? Two elimination reactions. We can do them both at once, okay, at the same time. How do we do elimination? Again, E2 elimination. What reagent? TB toxide. I mean, there's other bases you can use. You can use like LDA or stuff like that. But just T-butoxide. And then you can say 2 equivalents, right? You need 2 equivalents of T-butoxide. How does it go? See, here are the hydrogens, for instance, we are eliminating. Right, so 1 T-butoxide will come in, eliminate this one. That makes the double bond here. Okay. Then the other one, the other T-butoxide will then come in and eliminate. This happens in like 2 steps, right? So the other one will then come in and eliminate here. Okay? Does that make sense? Okay, so I'll take the second one away. Because it doesn't happen at the same time. Okay? The chance that all 2 T-butoxides come together with the molecule and in the same like tiny nanosecond will really do the reactions both at the same time. It's negligible. It's like winning the lottery. Okay? What's much more likely is 1 T-butoxide collides with the molecule, makes 1 double bond, and then that molecule swims around for a while as an intermediate and reacts with another T-butoxide a little bit later. Okay? So it is a 2-step process. Yes? Uh-huh. Oh. So you are saying you want to use a less sterically hindered base so that it makes the Zaitsev product. I think that would work, but I think in this case actually there's really no way. As long as you do just simple elimination, like, it doesn't matter where you can only get 1 product. Because you can only take off this hydrogen or this hydrogen. So if you took off this hydrogen, an extra bromine, let's see. Where do you see an extra bromine? Show me. Let's see. Oh, you mean this one? This one?
Yeah, this is third.
So if you took, okay, that's a good question. So if you took off that one, then you are still going to get the same, yeah. Oh, so you're not going to take off that one. Why? Because you make the more stable product, which is the conjugated double bond. Okay? That's a little bit complicated. So essentially, if you took off this proton, okay, this red one, you would get a double bond up here. Okay? Now if you get a double bond up there, these 2 double bonds are not in resonance with each other. And resonance stabilizes a molecule. That's why you're going to take off either this one or the other one here. That's because of resonance, okay? It strongly favors the resonance stabilized, the one with the 2 double bond, the diene which is conjugated. That's a good question. So, and you are right. Maybe if you formed a little bit of that as a side product, and using the methoxide would also work. Okay? It's a good question. It's a little bit almost beyond the level of the class. Okay? So, here, what happens? Okay, A. What's going on with A? It's doing a hydrogenation, okay? So we're going to go and write this product, hydrogenated, done. B, B, HBr addition, okay? Again, Markovnikov type HBr addition, so it gives you product like this, all right? C, bromine now in the presence of water. You get the bromonium ion, right, which gets opened up from the backside with water, so it gives you the bromohydrin. Okay, so now you have to be careful. This must be then a syn or anti-addition. It's an anti-addition, right, because you open the bromonium ion from the backside. Okay, so it's going to look. Let's see. The water, and the water is coming. So, for example, if this is the bromonium ion, right? If the bromine came from the front, Okay? Now the water is going to attack where? The water is going to attack the more substituted carbon, right? So it's going to be OH2. It's going to attack the more substituted carbon, open up the bromonium ion from the back side. And so that means the methyl group is going to point, here's our 5-membered ring, the bromine is going to point up, right? And the methyl group is going to point up as well. And then in the end, this after deprotonation, right? Then you get the water, the OH pointing back. Okay? And so now this clearly has an enantiomer, this is clearly has chiral centers. So here now you also form the enantiomer. Okay? Make sense? Now last one. What is the RCO3H doing again? It's making an epoxide. Okay? So it's going to look like this. One epoxide looks like this, where the CO3H comes from the front. So this methyl is pointing back. And now again here we have chiral center, right? We have 2 chiral centers, one here, one here. So this also makes the enantiomer. Does that make sense? Again, depending on whether the epoxide attacks from, or the peracid comes from the front or from the back. Okay? Any questions so far? Good. Now what else did we have? The acid catalyzed ring opening of the methoxide. This, so this was the, we're going to ignore the stereochemistry for now, right? This was the epoxide, okay? So it's acid catalyzed, that means it's H plus. The other mechanisms we already drew, right? So it's H plus, and you protonate the epoxide, right? This is pretty much literally out of the lecture notes. And you're going to get the protonated epoxide, which has a positive charge, of course, on the oxygen, right? And then, what is the acid catalyzed ring opening, okay? So then we have some water, which opens up the ring. And again, it goes on the more substituted carbon. And let's see. So then you get OH over here. Let's still draw in some stereochemistry, sorry. This is coming forward, right? So that means the OH here is pointing forward. And then the water came from the back side, okay? So it was an anti-addition. So that means the methyl now is pointing forward because the water came from the back. And so you get OH2 plus, all right? And then the final step, let me just write out, you can write it like this, okay? Because we need to draw one H so that you can then do the deprotonation, okay? So that gives us the final product here. Here we go. Okay, so the OH up, methyl, or the OH down here, right? Methyl up. Plus, the whole thing, the whole mechanism will work with the enantiomer. So all of these steps have an enantiomer. Does that make sense? All of these steps have an enantiomer. All right. Let's go to the next one. Let's see. Let's see how far we can get here. What do RS identify? Show examples. That you know, right? That you know. It's just RS, okay? So don't waste your time. Fischer projection of RS2-bromo-3-chloropentane. Okay? So how do you do this? You go like, you draw it, okay? So you do pentane. So you do 1 carbon, 2, 3, 4, 5. Okay? That's a pentane. Now 2-bromo, what I generally do if I have these kind of problems, I will just come up with one. I will do one example and then just pick randomly whether it's RS and then see whether it's RS and then fix it if I need to, okay? On scratch paper. So 2-bromo-3-chloropentane. Okay, so that means this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Okay? So now 2-bromo, let's put a bromine here on the right. Why not? And a chlorine here on the right. Now let's see if it's R or S. Right? These are H, 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 H. Sorry, wrong. See, I couldn't do this stuff myself anymore. So chlorine, this is CH3, H, 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 CH3, okay? Okay, so now, the question is it R or S on the first carbon there, on carbon 2? And you can look at it so that the priorities, right, are the bromine is coming forward, the H is coming forward, all right? And so bromine is priority 1. Then this carbon here, carbon 3 must be, so priority A is the bromine, priority B is this carbon, priority C is this methyl, priority D is the H, all right? Good? Now the easiest way to look at it is to look along this bond from the front, okay? You imagine looking along this bond and then the H is pointing toward you, so then in the end, you know, you want it to point away from you, but if it points toward you, you can just assign RS and then flip the thing in the end, okay? So you see BR, if you look along there, BR is A, then B, then C, so it rotates like this, which is R, so this means it's S, okay, what we drew. So that means the correct thing must be different. The correct thing must be like this. Okay, so the correct thing must be the bromine over here. Does that make sense? We'll finish this one, then I'll let you guys go. Now the Cl, let's look at the Cl, okay? That carbon 3. Again, this is priority A. This is priority B. This is priority C. This is priority D, I think, okay? So now you look at it again with the H coming toward you. A, B, C. So this is R. So this is correct. Oh, it's not? A, B, C. So that's S, right?
Yeah.
But then it's again, the H is again pointing forward, so it's R.
So you need
Oh, but it has to be S. Okay, so we have to flip it. You're right. Sorry. Okay, so the correct thing would be this. That's the correct thing. Okay, this is not correct. Okay, that's how you do this. All right? I think there were a couple other problems on there. Are there?
What if you looked at it from the other side? You have to indicate which side you're looking at it from. So you looked at it from the other side, and one of the first chocolate is incorrect.
Yeah. Okay, we'll see you guys on the final, okay? Office hours today, 3:30 to 4:30. Come by if you can, okay? Send me emails if you need any help. I'll see you guys.